Silicon, the base material, is extracted from sand. The extracted silicon then undergoes a purification process. This purification aims to create a nearly perfect crystal structure. High purity is essential for semiconductor performance. The purified silicon is used to create wafers for microchips. Purified silicon crystals are essential for microchip manufacturing. These crystals are meticulously sliced into thin, circular discs. These discs are known as wafers, the base for microchips. Each wafer acts as a substrate for hundreds of microchips. This process is critical in semiconductor device production. Semiconductor fabrication plants, or fabs, require extremely high air quality. This is essential to prevent contamination during chip manufacturing processes. Even microscopic particles can cause defects in semiconductor devices. Fabs maintain air quality standards, far exceeding those of typical clean rooms. The air in a fab is often 1,000 times cleaner than a hospital operating room. This level of cleanliness ensures the reliable production of high-quality chips. Photolithography is a crucial process in semiconductor manufacturing. It uses ultraviolet UV light to etch circuits onto silicon wafers. This etching creates pathways for electronic signals. These pathways form the complex circuitry of microchips. The process enables the creation of microscopic circuit patterns. Precise control of UV light is essential for accurate etching. Transistors are added to silicon wafers in multiple layers during chip manufacturing. Modern chips contain billions of transistors to increase processing power. Each transistor is smaller than a virus, highlighting miniaturization. This high density enables powerful computing capabilities in small devices. Metal connections are layered onto the semiconductor wafer. This layering links transistors and other components together. These connections form functional circuits within the microchip. The circuits enable the microchip to perform its intended functions. Insulating materials are layered to prevent electrical shorts in microchips. These layers ensure the proper function of the microchip circuits. Precise application is crucial for reliable performance. Insulation is a key step in microchip fabrication. After extensive processing, the semiconductor wafer is ready for the dicing process. Dicing involves cutting the wafer into individual rectangular dies. Each die represents a single integrated circuit or processor. These individual processors are the core components of electronic devices. For example, these processors can be used to power smartphones. The dicing process is crucial for separating the functional circuits. Smartphone displays use OLED or LCD tech for clear visuals. Manufacturing starts with ultra-thin glass sheets. These sheets provide a durable and transparent surface. The glass forms the base for display components. This ensures optimal viewing and protection. Transparent conductive layers are applied to glass sheets. These layers enable touch sensitivity on the display. The conductive layers also provide electrical conductivity. This is essential for the screen's functionality. Display panels create images and text using microscopic pixels. Millions of these pixels are manufactured on the screen. Each pixel is a fundamental visual element. The pixels work together to form the overall image. Precise control of each pixel ensures image clarity. This process enables high-resolution displays. OLED screens use pixels that emit their own light. Unlike traditional LCDs, this self-emission allows for vibrant colors and high contrast ratios. The absence of a backlight enables deeper blacks and better energy efficiency. OLED technology results in a thinner and more flexible display design. These features make OLED screens ideal for high-end TVs and smartphones. LCD screens use a backlight to generate visible images. The backlight shines through liquid crystals within the screen. This process necessitates additional layers for proper illumination. These layers ensure even light distribution and optimal image quality. Protective glass is applied to screens for enhanced durability. The primary purpose is to prevent scratches on the screen surface. It also protects against damage from regular daily use. This added layer acts as a shield against impacts. It helps maintain the screen's clarity and responsiveness, ensuring longevity and optimal viewing experience. A touch-sensitive digitizer is integrated into the smartphone screen. The digitizer's primary function is to detect and process user input. This input is typically in the form of touch gestures on the screen. This enables interactive control of the smartphone's functions and applications. The display panel is carefully aligned during screen assembly. Proper alignment is crucial for a functional screen. The panel is bonded to other layers in the assembly. Bonding ensures a seamless connection between layers. This process results in a complete, functional screen. Adhesive bonding is used to secure the layers of a screen together. This process ensures that all layers are firmly attached. The adhesive creates a strong connection between the screen's components. This method results in a robust and unified display unit. The bonding enhances the screen's structural integrity. It helps to prevent separation or damage to the screen layers. Finished screens must meet stringent quality standards. A key requirement is achieving an ultra-thin profile. Brightness is essential for clear visibility. Durability ensures longevity and reliability. Energy efficiency is crucial for lower power consumption. These standards ensure high-performance displays. Screen quality control is essential to ensure product reliability. Screens are inspected for defects like cracks and dead pixels. Screens with cracks are rejected to prevent structural failure. Screens with dead pixels are also rejected for visual defects. Rejection maintains high quality and prevents user dissatisfaction. Lithium-ion batteries are commonly used in smartphones and other portable devices. Their popularity stems from their high energy density relative to size. Lithium-ion batteries also have a relatively long lifespan. They are designed with safety features to ensure safe charging. These combined advantages make them ideal for mobile applications. Battery production often takes place indoors. Lithium cells are sensitive to moisture. Humidity-controlled rooms are essential. These rooms prevent moisture damage. Controlled environments ensure battery quality. The cathode is the battery's positive electrode. It's made from thin layers of cathode material. These layers are stacked precisely. Alternatively, they can be rolled together. This forms a compact, layered structure. This structure is essential for battery function. Battery assembly involves creating key components like the anode. The anode functions as the battery's negative electrode. Thin layers of anode material are used in its construction. These layers are carefully stacked or rolled together. This process forms the complete negative electrode structure. Electrolyte is introduced between the cathode and anode layers. The electrolyte acts as a medium for ion transport. Ions flow through the electrolyte during battery operation. This ionic flow enables the battery to conduct electricity. The battery is enclosed within a protective layer. This layer can be a flexible pouch or a rigid metal casing. The primary function is to shield internal components. Sealing prevents damage from external factors. It also ensures the battery does not leak its contents. This sealing process is crucial for battery safety and longevity. Overcharge tests assess battery safety under excessive charging conditions. These tests verify the battery's ability to manage high charge inputs. The goal is to prevent overheating and potential explosions. Safe handling of overcharging is critical for battery reliability. Heat resistance tests assess battery performance in high-temperature environments. These tests verify the battery's ability to function without degradation. The goal is to ensure stable operation under extreme thermal conditions. Degradation can include reduced capacity or increased internal resistance. Passing these tests confirms the battery's suitability for demanding applications. Short-circuit simulations evaluate battery safety during electrical faults. These tests mimic scenarios where an unintended electrical path occurs. The goal is to observe how the battery responds to such events. Data gathered helps assess the effectiveness of safety mechanisms. These mechanisms are designed to prevent thermal runaway or explosions. This ensures safe operation and prevents potential hazards. Smartphone batteries must meet strict safety standards before approval. These standards ensure user safety and device reliability. Approved batteries undergo rigorous testing to verify performance. Testing includes thermal, electrical, and mechanical stress assessments. Only batteries passing all tests are deemed safe for smartphone use. This approval process minimizes risks of overheating or malfunction. Robots are used to assemble smartphones on an automated assembly line. The motherboard is a critical component placed onto the smartphone frame. The motherboard houses essential elements, including the processor. Memory chips are also mounted on the motherboard. Other integrated circuits and chips are affixed to the motherboard. Robots ensure precise and efficient placement of these components. Robotic assembly lines automate precise manufacturing processes. Tiny robotic arms manipulate components with high accuracy. Microscopic amounts of solder connect components on motherboards. This automation increases production speed and consistency. Robotic assembly lines use high-speed cameras for quality control. Cameras inspect each connection to ensure proper soldering. Inspection aims to identify and prevent defects in real time. This ensures high standards and reliability in the final product. The battery is a crucial component for smartphone operation. It provides the necessary electrical power for all functions. The battery is carefully inserted into the smartphone frame. This insertion is typically automated in modern assembly lines. Robots ensure precise placement and secure connection. Correct battery installation is vital for device functionality. A robotic assembly line efficiently integrates various components. Cameras are added for visual input and object recognition. Speakers are incorporated for audio output and alerts. Vibration motors provide haptic feedback or movement. Antennas enable wireless communication and data transfer. Each component serves a specific function in the final product. Robotic assembly lines require extreme precision in component placement. Components are often placed within fractions of a millimeter. This level of accuracy is crucial for ensuring proper functionality. Robots use advanced sensors and control systems for accuracy. Precise assembly minimizes errors and maximizes product quality. The phone display is carefully aligned with the phone body. Industrial presses are used to join the display and body. These presses apply controlled, even pressure. This pressure ensures a secure and precise fit. The process creates a tight seal between the components. This seal protects internal components from damage. Robotic assembly lines automate smartphone production. Smartphones are fully assembled in a matter of minutes. Robots ensure precision and speed in the assembly process. Assembled phones proceed to testing and quality control. Automation enhances production efficiency and reduces errors. This streamlined process ensures consistent product quality. Modern smartphone factories operate on a massive scale. These facilities are designed for high-volume output. Some factories produce hundreds of thousands of smartphones daily. This demonstrates the efficiency of modern manufacturing processes. Automated machines rigorously test phone button durability. The machines simulate thousands of button presses. This ensures long-term button reliability. Responsiveness is also tested during the process. Touchscreen quality control involves rigorous testing of display functionality. Simulated swipes are performed to evaluate touchscreen responsiveness. These tests ensure accurate function across the entire display area. The goal is to verify consistent performance and identify any dead zones. This process guarantees a high-quality user experience. Charging cycle tests assess a battery's ability to charge and discharge. These tests simulate repeated charge and discharge processes. The goal is to verify proper battery function over time. This ensures the battery meets performance standards. Quality control includes rigorous charging cycle testing. These tests are crucial for assessing long-term battery health. Drop tests evaluate a phone's ability to withstand damage from accidental falls. These tests simulate real-world scenarios where phones might be dropped. The goal is to assess the phone's structural integrity after impact. This ensures durability and longevity for everyday use. Environmental chambers simulate real-world conditions for phone testing. These chambers expose phones to extreme temperatures. High heat conditions are replicated to test phone durability. Freezing cold temperatures are also simulated in testing. Humidity levels are controlled to assess phone resistance to moisture. Cameras undergo rigorous testing to guarantee high-quality image capture. Focus is a critical parameter assessed during camera testing procedures. Sharpness and clarity are also key factors in evaluating image quality. The goal is to ensure images are crisp and detailed, meeting quality standards. Testing verifies the camera's ability to produce clear, well-defined images. This process helps identify and correct any focus or clarity issues. Microphones undergo testing to ensure accurate sound capture. Speaker analysis verifies clear audio output during playback. Testing aims to provide optimal audio during calls. The goal is to deliver high-fidelity sound for media playback. These tests ensure overall audio clarity and fidelity. Wireless signals undergo thorough testing to guarantee reliable connectivity. These tests are conducted within specialized radio frequency (RF) shielded room. RF rooms are designed to minimize external interference. This controlled environment ensures accurate and consistent test results. The goal is to validate the performance and stability of wireless connections. Quality control involves rigorous testing to ensure product standards. Phones undergo a series of tests during the quality control process. Any phone failing these tests is immediately rejected. Rejection maintains high product quality and customer satisfaction. After passing quality control, the smartphone undergoes a thorough cleaning process. This cleaning stage is essential to remove any dust or particles accumulated during production. Following cleaning, the device is carefully polished to eliminate any blemishes. Polishing ensures a flawless surface, enhancing the phone's aesthetic appeal. This attention to detail guarantees a pristine product presentation for the consumer. Software installation prepares a smartphone for customer use. The installation process configures the device's core functions. It also loads essential applications for initial operation. This setup ensures the smartphone is ready upon activation. The packaging process involves adding various accessories to the box. These accessories typically include charging cables for power. Essential documentation is also included, such as user manuals. A SIM card ejector tool is added for accessing the SIM card slot. All accessories are carefully placed inside the box. Finally, the box is sealed to secure the contents for shipping.